All right, everybody. So I'm gonna make a video that kind of shows y'all how factoring works. And yeah, I'm standing in front of the whiteboard because I'm tired of sitting down. So we've sort of started working with quadratics before now. And basically all of Unit 3 in algebra is this idea of quadratics. And really, it's just kind of the next step in what we've already been doing, which is this idea that you can relate two variables together, and depending on what you do with those two variables, they create different patterns, and you can use them to model different situations. Most of what you've seen so far has been straight lines, linear, but now we're going to actually start working with this idea of quadratics, which just means that you have a parabola, basically. So you have a U-shaped graph. So we talked about this when we were multiplying polynomials. We introduced like the box method there, went through how we multiply variables together, how we combine like terms. And essentially when we start talking about this idea of factoring, we're reversing the multiplication that's already happened. But it's not always that simple because you have multiple terms in a polynomial. And so when you start trying to break apart multiple terms, it just winds up being a little more challenging sometimes. So I'm going to start with just kind of like a basic introduction to what we're doing. So what is a quadratic equation? And I say that loosely because, obviously you see what is a quadratic equation. You see that a lot because equation just tends to be the term that gets tossed around, but technically all equation is really telling you is that we have an equal sign. It could be a quadratic expression. Some quadratics are functions. And then you also have this word parabola that gets tossed around. So rather than just having equation, you could see expression, you could see function, and there are differences. I mean, function is telling you, again, it has that one input with a specific output, or only one output per input rule. In other words, your inputs can't repeat if you're listing out all the points that are there. Expression implies that there is no equal sign. Equation implies that there is an equal sign, but basically all of these are the same pattern, just different little scenarios. And then the word parabola, to clarify, that's parabola, not parabola. Some people say parabola, that's parabola. That's referring to what we call the graph. So when we start working with quadratic equations, quadratic, if you think back to when we were naming polynomials, quadratic referred to a degree of 2. So if your degree equals 2, it's quadratic. And remember, degree just refers to the largest exponent on a polynomial. So in other words, anything that features x squared is a quadratic. And when you graph a quadratic, it creates this item called a parabola. So I'm just going to make up one right here. We're just going to say like x squared plus 5x plus 7. Okay. So that is a typical polynomial that you will come across when we start talking about quadratics. It's a trinomial specifically because it's got 3 terms. And we could potentially be asked to graph that. We could potentially be asked to factor that. But that's what they look like. And basically the idea is we should be able to break them into factored form. In other words, some sort of multiplication happened to get here. Let's go backwards and figure out what that multiplication was. But before we even like dive into that, it's helpful to understand why we're even trying to do that in the first place. So kind of bearing all that in mind, I'm going to show you all just a very generic example here. So I have a graph, and let's say I just put a parabola on it. Let's see how my other colors do. I'm going to try to use blue to do this parabola. So let's say I put a parabola on here that looks something like this. Okay. So sometimes you'll hear people call it the big U. Well, that's why, because it looks like a U. This is X, this is Y, of course, X-axis, Y-axis, and that's our graph. There are certain elements of that graph that you'll be asked to identify, which we'll talk about. But basically, some of it's familiar and some of it may not be. So wherever this parabola crosses the x-axis, you have these points here. Those are your x-intercepts, just like they would be with a straight line. But notice there could be two, and in this case there are. And we call that an x-intercept, but that's not the only term that can come up to describe those now. Sometimes it'll be x-intercept. Sometimes you'll be asked to find the roots. Roots mean the same thing. Sometimes you'll be asked to find the zeros. And again, means the same thing. If I ask you to find the x-intercepts, if I ask you to find the roots, if I ask you to find the zeros, I'm asking you to find the same thing. Turns out to factor, the reason why we even start talking about factoring, which is where we're headed, the reason why we start talking about breaking down these equations when they appear like this is because if you can factor them, you can find this information. It turns out that this information here, where these parabolas cross the x-axis, winds up being very important. But that's not all the information that's here. You have a vertex as well. And the vertex will be the lowest point of the parabola, which is going to be somewhere kind of like right in here, actually. Not quite in the center. I didn't quite center it, but your vertex is always going to be either your lowest or your highest point. In this case, and let me kind of adjust this because that doesn't look right. So your vertex on this parabola should be somewhere kind of here, more like. So not quite on the y-axis, but next to it. And that little point there, which is your vertex, again, it's either going to be the lowest point on your graph or the highest point on your graph. In this case, it is the lowest point on your graph. And I'm just going to write this out to the side. That way I know everybody can see it. So we call that vertex. But also, too, in this case, since it's the lowest point on the graph, it's technically also called a minimum. Now, the flip side of this, literally, is that there's no reason why we can't have a parabola that does this. Well, if you've got a parabola that does that in red, it still has the same features. I mean, you've still got these x-intercepts. You've still got a vertex. It's just that now your vertex is up here. And instead of being a minimum, it's the highest point. It's your maximum. The only other really information here that I want to point out, sometimes some of your critical points, as they're called, can like take on the same value in a problem. So like, for example, your vertex is really close to the y-axis here, but it's not quite there. If your vertex was actually on the y-axis, it would still be your vertex. It's just that just like this has x-intercepts, it's technically got a y-intercept too. So wherever the parabola crosses the y-axis is your y-intercept. So I'm just pointing out that like it could wind up being like the same value as your vertex, but both of these I drew slightly off center. So technically their y-intercept is going to be not the same point as the vertex, just kind of near it. The thing to remember though is that with your x-intercept, your x-intercepts I should say in this case, remember the value of y at your x-intercept is going to be y equals 0. And similarly, when you do find your y-intercept, the value of x there would be 0. And that's just because, as we talked about before, technically the x-axis, the equation that describes the x-axis is y equals 0. the equation that describes the y-axis is technically x equals 0. Okay. I would encourage you to like pause this video as you need to take notes, but I'm going to kind of keep going. I'm going to erase all of this now and show you one other part of this graph that matters. I'll leave our little header up there, but I'm going to make a bigger graph now. And I'm not going to do a specific example, but I am going to do like an illustration here. So this is x, this is y, and if we have a parabola on here, we're just going to make a nice big parabola that does something like this. Okay, so like we were just talking about, there's a vertex on here. It's going to be your lowest point, which is somewhere right about there. So again, vertex. Well, it turns out the vertex is going to be, because it's either your lowest, in this case, or your highest point if the parabola was upside down. Because it's either lowest or highest, it also centers itself perfectly like in the parabola, which means that your parabola is going to be symmetric actually on either side, which I just kind of want to point out that sometimes it's hard to like draw it symmetrically, but it is. And so there's also this other feature of the vertex, which is if you can find the x value of the vertex, which you would need to say what it is anyway, because like your vertex, just like any other point, is going to be xy. Well, if you can find that x value, then you can also write the equation of a line that goes straight through the vertex. So to kind of tell you what I'm talking about here, vertical lines are described by x equals some number. So like if, for example, this vertex was, I don't know, let's say that's 2. If this vertex is at 2, and I don't know, let's say that's -5. Okay, so instead of saying xy, I'll literally say, well, this vertex is at 2, -5. Just made that up. But here's the thing. If I said, okay, draw a line that cuts this parabola in half, your line would go through here. And that line has a name. That line is called the Axis of Symmetry. And it's called the Axis of Symmetry literally because when you draw that line, you're saying that your parabola is symmetric about it. So it like matches on either side. That means that your y values on either side of the parabola should match. Your x values on either side of the parabola will be opposites of one another. Oh, and the way you find the axis of symmetry, the way you describe it, if this vertex is at 2, -5, then that line is simply x equals 2. And that's how you describe your axis of symmetry. Okay. So that's kind of visually what's going on. That's kind of like the important pieces of your parabola. And there are more bits of information that'll kind of come up as we go. But now we're going to take a moment to kind of dig into some of these equations. And if you needed what I just erased, don't forget this is a video. You can rewind. So feel free to pause. So you get the idea of what the graphs look like. We're basically making these curves. And why are they important? Why do they show up? One of the best applications I can think of is like, let's say, I'm going to use green here. Let's say we have this nice grassy area, right? See, we've got this nice grassy area that goes all the way across. Only it's about to get more interesting because instead of this just being like a grassy area, well, actually, we have like some kind of suddenly we have a missile launcher, right? And those are really fun. And if we shoot a missile, it's gonna go up, and we'll just assume it's trying to hit a ground target. It's gonna come down. To be fair, even if it wasn't trying to hit a ground target, it would eventually run out of fuel. It'd still come down. So for the most part, they make an arc. So if we visualize this as an XY graph, then this would be like your y-axis, and this would be like your x-axis, potentially. And I mean, your y-axis may be somewhere else, but you get the idea. You can think of this as being on an axis. So it then follows that it's pretty useful to know where it hits the ground. Just like it's pretty useful to know where it came from. So like, this is just one example of an application. If we can find the equation of this parabola and figure out the x-intercepts in like a real world problem, we could literally say, this is where this missile's going. This is where it came from. And maybe this isn't your y-axis. Let's say for a second, this actually isn't your y-axis. In fact, let's do this. Instead of this being your y-axis, I just decided that this is our axis of symmetry. So that's the vertex of our parabola. And I don't know, maybe your y-axis is actually back here. Which again, completely okay. It doesn't matter, just letting you know that this is on a grid. So if this is our axis of symmetry, now you can think of like other applications, like when would the missile be at its highest point? At the vertex. If we, over here on the ground, can stop a missile, but only before it gets to its highest point, then I could figure out how much time I had before it got to its highest point, et cetera, et cetera, et cetera. So this is just like an example of why we're really interested in finding these beginnings and endings. And it's not just missiles. Anytime you throw something in the air, anything that has parabolic motion, anything that makes a parabola, it's going to follow these equations. All right. So with that said, the issue is that when we really start diving into equations and calculations, most of the time, we're not really using graphs. I mean, they're useful to have like in an application, but we don't always have them. And so you need to be able to manipulate the numbers and the variables. I mean, if you always had a graph, then you could just find the points on the graph, good, we're done. But you're not going to have a graph. So what if we don't have a graph? Like, what do we do? And that's kind of the idea behind what we're working on now. So I'm going to erase our title here, and we're now going to talk about two ideas. One's called standard form, one's called vertex form. Before we do that though, the only other piece that I kind of want to give you is this. This is very generic, like y equals x squared is the most basic of all the parabolas. And y equals negative x squared, same thing. But just realize that when it's positive, if I graph it, it looks like a U. If it has a negative in front, when I graph it, that's what makes it upside down. So actually, like our missile example, it would have been a negative one because it's curving like this. On the other hand, like somebody diving, going under the water and then coming back up would probably be a positive parabola. Okay, so now we're going to talk about these forms. So their standard form, which is probably the most common. And it's actually pretty straightforward in that it follows kind of like a similar pattern that you're used to looking at if you remember standard form of a line. But we're talking about a parabola here, not a line. So specifically, we're talking about a quadratic equation. Sometimes you'll see it written with y equals, sometimes you won't. It's okay. Just realize that we have, and I'm going to try to color code this, x squared plus x plus. And the standard form is this. You get ax squared plus bx plus c. And that's really important because that a, b, and c, winds up being information that we can use. That's standard form. And then there's also vertex form, which introduces two new variables just because it wants you to not get confused with what's going on up there. But it's y equals a x minus h squared plus k. All right. So, and I'll tell you what, I'll do h and k in a different color just to be consistent with what I did up there. All right, h and k. So a, b, and c up there are important because they're the numbers that go with our variables, and then c is our constant that hangs out. In standard form, c is your y-intercept, actually. So whatever c is the y-intercept. These, on the other hand, technically they're coefficients. A is the coefficient on your leading term, x squared. B is the coefficient on x. Down here is a little bit different. The reason why we like this is because h, k, as the title kind of suggests, is your vertex. There's a third form called factored form, which if you factor it, that's what you put it in. So like I don't usually teach factored form as a standalone thing. Just realize that once we factor something, you've put it in a different form. It's easier to factor things that are in standard form. Arguably easier to graph things that are in vertex form. So these have different uses. If we're trying to graph a parabola, this is pretty helpful because the vertex, as you remember, it's either our highest or our lowest point. So like you get the middle of the graph immediately. And if it's positive, you know you've got a u doing this. If it's negative, you've got an upside down u. With standard form up here, one of the pieces of information that comes from this is that you can actually find, so here if you need the axis of symmetry, remember it goes through the vertex, well you've got the vertex. So the axis of symmetry will just be this. X equals h is AOS, which is axis of symmetry. Because the axis of symmetry is just whatever comes through that h value, because that's your x value at the vertex. Well, with standard form, it's not so simple, but there is at least an equation that we can use, which is x equals and again, I'm going to color code this just so that you can see where it comes from. All right, so x equals negative b over 2a. So down here, if it's in vertex form, you can find the axis of symmetry just from it because it's there. Up here, if you've got it in standard form, you can find the axis of symmetry by using this formula. Okay. So that has been sort of your crash course intro, if you will. So what quadratics are, and now we're going to start going into how we factor these, like how we actually work with this information, how we break them apart. This would be a good place to pause if you need to, and then we're going to continue on with some examples. Okay, so example 1. And on all of these, our goal is going to be factoring. But you'll get different instructions. I mean, sometimes it'll say like factor the expression. Sometimes it'll say factor the equation. Sometimes it'll say factor completely. Sometimes it'll just be like find the roots or find the zeros or put it in factored form and not even tell you to factor, but like the only way you can do those things is to factor. With example 1 though, we're going to start with kind of some special cases that can occur just because it's worth knowing these 2 special cases. So I'm going to start with these 2 special cases. And honestly, you know what? I'm not even going to call it example 1. I'm literally just going to call this special cases. I'm going to let our examples actually be the deeper problems So special case 1 is dots, which is a nice abbreviation for difference of two squares. Now, the idea with this is that if what you're multiplying to get your polynomial, like if what was multiplied to get the polynomial fit a certain pattern, then maybe there's a pattern we can use to factor it. A difference of two squares is one of those scenarios. So just to like recall, if I have x plus 5 times x minus 5, you should be able to multiply that. Now, if you don't remember how, I mean, it's okay, but not really. You really need to be able to do this. And there's different ways to show it. Some people use the box method, some people don't. I will show you how to use the box method here, but just know that the further you go in this, you're gonna probably have to stop relying on this if you are. So to multiply these, you can set up a box like I did. I'm gonna fill in the box in red. So x times x is how you fill in this first box. You just look at what lines up. X times x is x squared. X times 5 is 5x. X times negative 5 is negative 5x. And 5 and negative 5, when you multiply them, gives you negative 25. To finish that multiplication, you have to add everything that's in the box, which means you're going to combine like terms. So you get x squared, and then the 5x minus 5x cancels when you add them. So you just get x squared minus 25. Okay. If you didn't want to do the box method and you just want to multiply these as is, there is this thing called FOIL which you can use, which I don't like because it only works if you have a 2 by 2 like this. So if you reach a point where you don't have a 2 by 2, meaning two terms, FOIL does not work. It's better just to think about it as like double distributing. So 5 needs to be multiplied by x, and it needs to be multiplied by negative 5. And then you do the same thing with this x, and then you add it all together. So you get x squared minus 5x, I did the one on the bottom first technically, and then plus 5x minus 25. And you get x squared minus 25. Honestly, they both take up about the same amount of space. I don't care which one you use. So you should remember that you can do that. And so it's called a difference of two squares because your solution that you got here was literally a difference of two squares. X squared is literally x times x, so it's a perfect square. It's x times x, it's x squared. 25 is a perfect square because that's 5 times 5. But now, for factoring, like we don't want to do this. We want to be able to take what you're given and work backwards. And so basically, if you have a special case like we do here, it's just really fast. Because if you recognize that you have this difference of two squares, like if I'm asked to factor this, then I look at that and I go, oh, it's a difference of two squares. Here's the answer. Done. I factored it. Now the thing is, I didn't just make that up. Like, I know that's what I started with because I did it over here. But say you didn't have this information. The reason you're able to do this is because there's a pattern that you can follow. And the pattern specifically, I'm going to write it down here. I'm going to put it in blue. That way it's in a different color. So the pattern is simple. It says if you're trying to factor, you know, it's really not even saying if you're trying to factor. It's just literally telling you if you have a squared minus b squared, that's the same thing as having a plus b and a minus b. That's your pattern. Well, it turns out that that's factored form over here. So if you recognize a polynomial, in this case, it's technically a binomial. It's quadratic because it has degree 2. X is a perfect square, 25 is a perfect square. They're being subtracted. So X is A, 25 is B squared, so 5 is B. So if I do X plus 5 and X minus 5, it's equal. Well, I can do that, and it turns out that's in factored form, so I've factored it. That's just how difference of two squares works. The other thing you can run into is this idea of a perfect square trinomial, sometimes abbreviated PST. It's a perfect square trinomial. And honestly, they're like it's a similar conversation. I'm going to show you how to multiply again, but I'm only going to use one method now. So if you had like x plus 5 times x plus 5, remember that's the same thing as x plus 5 squared. Well, because you have the same terms here, an x plus 5 and an x plus 5, kind of like with that difference of two squares, because you have the same terms here, like previously with the difference of two squares, you had x and 5, but it was just one was plus, one was minus. Well, here, you've literally just got the same binomial written twice. So just like with the difference of two squares, it follows a pattern. So if I want to multiply this out, and I showed you this because sometimes it'll be written that way because these mean the same thing. If I want to multiply this out, and I'll use green, this time, since it's not opposite signs, your middle term doesn't cancel. So you get x squared plus 5x plus another 5x plus 25. And then when you fully combine like terms here, you get x squared plus 10x plus 25. So this is what you get here. But kind of like I was saying before, there's a pattern to be seen here. The question is, can we find the pattern? And it's not always obvious, but I'm going to take the time to kind of show y'all what the pattern is over here. So we just determined that x plus 5 squared equals x squared plus 10x plus 25. So I'm going to use the a's and b's again, and honestly that is usually how it's done. I'm going to use the a's and b's again to show you the pattern. It'd be fun if I just asked you to find the pattern, and honestly right now maybe that's something you should do. Try to find the pattern, because if you can, it'll help you understand how it works. But basically, this is like having a and b. So x is a, 5 is b. And if that's true, then this is like a squared. This is like b squared. And then you've got that 10x. And so the question basically is just, well, where does the 10x come from? And well, it's based again on the x and the 5. Specifically, it's 5 times x times 2. So this is plus 2ab plus b squared. So there you go. So if you have a plus b squared, it equals that. And the reason why I'm showing you that is because if you're asked to factor it, you're just doing the same thing, just backwards. So if you recognize the pattern immediately, like if you were given this and told to factor it, this is what you would be given, and your answer would be this. Or, you could write it out if you wanted to. So again, it's a pattern. It's helpful. Now technically, and I figured this out from looking through an old book actually, I have an algebra book that's like literally from the 80s. And it's interesting because I can pretty much use all of it in this class still if I want to. But there's actually patterns for most types of factoring that you do. It's just a lot to remember. And at some point it's like, okay, let's stop worrying about patterns and let's just use a technique that always works. It's worth these patterns. The techniques I'm going to show you on the polynomials that don't fit these patterns would actually still work on them. Like the technique you're going to learn in a little bit still works on these types of problems, but it's so much faster to just realize like, oh, it fits this pattern, boom, I've got my answer. Like literally there's no work to even show really. And I wouldn't ask you to do that, to show work here. All right, so that's your perfect square trinomials. There is one other thing that can happen here. I'm gonna erase what we just did, but I'm gonna keep the red right here, and I just want you to realize that this could also happen if you had a minus b squared. It also follows a pattern. A squared minus 2ab plus b squared. So in other words, instead of this being x plus 5 times x plus 5, had it been x minus 5 times x minus 5, again, the same polynomial times itself, the same binomial specifically times itself, it follows a predictable pattern. And the only thing that changes would have been here, this would have been a minus 10x. Okay. So those are your special cases. Not going to spend any more time going over those. You just got to be able to apply those formulas. And if you can't apply those formulas, guess what? You can still do it with the method that we're about to learn. Okay. So rather than having preset examples, I'm actually going to kind of go through and create these with y'all because I want y'all to actually kind of experience me working through them. I mean, there is one specific example that I do want to show you just because it's a little more challenging. But for the most part, again, I want y'all to experience, you know, me working through things. So this first example, example 1, and this is just going to be like our general factoring method that works for everything. And if you want to give it a name, technically, you can call it the AC method. Sometimes you'll hear it called like the X method, and you'll see why. All right, so example 1. Let's just say, and again, I'm going to show you the multiplication on this one, and then from this point forward, I'm going to stop showing you the multiplication. So like, let's say I had 2x minus 7 times 3x plus 4. Okay. Obviously, this is not a factoring problem the way it's presented. It's a multiplication problem. But if we wanted to do this, then you do 3x times 2x. You get 6x squared. You do 2x times 4, which is 8x. Negative 7 times 3x, which is minus 21x. That's kind of interesting. And then negative 7 times 4, which is minus 28. Okay. If we, I guess I'll go ahead and simplify it actually. So then you get 6x squared. Combine like terms, an 8 and a 21 makes a 13. But that's a negative 21, so it's a negative 13x minus 28. Okay, so before we go on, there are some things I want to point out to you. If you think about these as having been multiplied, then it'll help you work in reverse and factor. Because basically, like this 6x squared right here, it had to come from somewhere. And in this case, like it literally came from 2x being multiplied by 3x. That's how you got 6x squared. Likewise, the negative 28 specifically came from multiplying negative 7 and 4. So when you go to factor these, like those are clues. Like when I try to factor this, 7 and 4 might be in my answer. 3 and 2 might be in my answer. But the bigger these numbers get, the harder it is to figure that out just by guessing. Because like, how do I know that if I was just given this, how do I know that was 3 times 2 and not 6 times 1? Or how do I know this is 7 times 4 and not 28 times 1? Or like as another example, let's say maybe like one of these numbers was 36. Well, what do you multiply to get 36? Is it 6 times 6? Is it 36 times 1? Is it 18 times 2? Is it 12 times 3? I mean, there's a bunch of options. So that's where like needing a technique comes in, because if you just start trying to guess what was multiplied to figure this out, it's difficult. And it turns out like the part of this that makes the least amount of sense when you first glance at it is actually what helps you figure out the answer. And what I'm referring to is this thing in the middle, negative 13x. It's obvious that 6x squared is 3 times 2. It's obvious that negative 28 is 7 times 4. It's not obvious where this comes from. Like we know because we just did it, but I'm saying like if you just had this, you wouldn't know that it was 8 minus 21. Like you would just know I've got a negative 13 and like look up here at these numbers. How do you get negative 13 out of this? I mean, there's a way, but it's not as simple as looking at it and being like, oh, 3 times 2 or negative 7 times 4. So that's actually where the challenge comes in. It's like, how do we break this middle term apart? And if you can break this middle term apart and get back to this point, like we can go from here up. There's no issue with going from here to there. The issue is going from here back to here. So let's do that. So you've seen this multiplication. I'm gonna leave it right here. Hopefully I've got enough room on the board. And now I'm gonna give you this problem. So this is how your problem would actually be presented. You'd have 6x squared minus 13x minus 28, and you'd be told to factor it. It might say factor completely. It might just say factor the expression since there's no equal sign up here. But that's a good example of a problem you would get. And we could guess, like, because that's exponent of 2, like I know my answer's gonna look something like that. But beyond that, I mean, I would just have to start guessing. Like what numbers give me this information? And don't get me wrong, I mean, you could eventually figure it out. Like you could say, well, this is 3 and 2 and 7 and 4 and eventually figure out what combination worked. But by the time you do that, unless you just happen to do it correctly on like the first try, by the time you go through all the different combinations and figuring it out, you would have done a lot of work. So let's not do a lot of work and let's get straight to the answer. And we're actually going to rely on standard form to help us do that. So if you recall, standard form is ax squared plus bx plus c. And people get this mixed up a lot. So I wrote it, but now I'm going to write it a different way on purpose. A is lined up with the 6. B is lined up with the minus 13. C lines up with the minus 28. It refers to the numbers. X squared is already there in standard form. X is already there in standard form. The A, the B, the C refer to the numbers, not the variables. And basically there's a pattern. There's a pattern. And it's not like it was just invented. It's just like knowing that to multiply these, something had to be multiplied and then combined. You can kind of work backwards, and this is how you do it. Sometimes people want to do it this way. And if you want to do it this way, that's fine. Sometimes people want to do it this way, which is also fine. And I know right now you're thinking, what in the world is going on? So it turns out that if I want to factor this, if I can find two numbers that multiply to give me A times C, and two numbers that add to give me B, I can figure it out. This is just a graphic organizer that says the same thing. It says, well, I can put A times C up here and I can put B down here. And on either side would be the numbers that fill in the blanks up here. Again, this is an either or situation. Some people just like to write it out like that. Some people like the graphic organizer style. I don't care. It does not impact your answer in any way. It's just two different options for doing the same thing. All right, so it would help to know what A times C is. And I'm going to wind up having to erase some information here. So just kind of bear with me. But I'm going to use this space to figure this out, and then I'm probably going to, I think that's what I'll do. I'll use this space to figure this out. And once we figure it out, I'll probably just write like the organizer down here, and then I'll erase this and write here. I'm just telling you that in case you're taking notes. All right, so A times C, well, A is 6 and C is negative 28. So 6 times negative 28 is our A times C. And I don't know what that is off the top of my head. That's when you use a calculator. So 6 times 28 is 168. So that's negative 168, which means that's what goes here. And your B is just whatever's there, negative 13. If you're going to use this graphic organizer, you would just put this on top and this on bottom. And sometimes people like to remind themselves that, like, I add to get what's down here, I multiply to get what's up here. I don't care. Again, like, it does not matter to me. And I'm saying it that way because I know sometimes teachers are like really specific. Like, I just want you to get the answer in a way that you do on your own that involves you using your brain and not a computer. So it's okay with me whichever way you use. All right. The challenge now, of course, is going to be what numbers multiply to give me 168, but add to give me 13. And this is what you're going to want to do. Make a chart. Now, if it's a smaller number, it might be obvious. But if it's not a smaller number, it's not going to be obvious necessarily. So 168, I mean, it's not going to be 168 divided by 1, because 1 times 168 works. But you don't add those and get negative 13. But I'm going to put the information on here anyway. So negative 1 times 168 is one way you can split that up. Negative 2 times 84 is another way you can split that up. Again, if we add these together, though, we do not get negative 13. So those are not the numbers we need. Can I divide 168 by 3? Yes. Negative 3 and 56. Again, though, if you add those together, it doesn't give you 13. 168 divided by 4 also works, negative 4 and 42. Same story though, they don't add to give you 13. Can't divide 168 by 5, what about by 6? You can, it's negative 6 and 28. Same thing though, they don't add to give you negative 13. If I go then to 168 divided by 7, I get, oh look, 24 and 7. So negative 7 and 24, which is close, but not it. 168 divided by 8 is 21. Negative 8 and 21 is how I do it. Okay. But if I add negative 8 and 21, I get positive 13. I need negative 13. So actually, it needs to be a negative 21. So went through all of that, but I found two numbers that fit the bill. And again, depending on how big the number is, this could take a little while. It may not take any time at all. 8 and negative 21, 8, negative 21, 8, negative 21, 8, negative 21. Okay. So the reason why I went through all that trouble, if you've been paying attention, those numbers should seem familiar because we already saw them before right here. So the way we work backwards to get to where we were when we multiplied is by looking for this pattern. What numbers multiply to give me A times C, but add to give me B? And once you find them, that's what we had. All right, so as promised, I'm going to put like this in the bottom corner so that we have it. I'm erasing everything else. And actually, I'm going to put it here because we've got room over here. All right, so I put it here. That way you remember what we're doing. And now I'm erasing all of this. All right, so why did we do that? I'm going to erase this too. Why did we do that? Because now we can actually break this apart and factor it. We can say, okay, so 6x squared minus 13x minus 28. Basically what we were trying to do, and I didn't explain it this way because I wanted to get there first, but basically we're saying, all right, like how do we actually split that negative 13 up? Because you can imagine there's a bunch of different ways to do it. Like that could be negative 20 and 7. It can be negative 21 and 8. I mean, there's literally infinite possibilities. And this is the only combination that worked. So we needed a way to get there. So now you just write it out by expanding it. So 6x squared plus 8x minus 21x minus 28. And there we have it. It's back here again. The reason why we want to do that is because now we can actually factor it and be done. How do we factor this? This is called factoring by grouping, actually. And basically, it's just doing greatest common factor, which I've already done. So if you find the greatest common factor here and the greatest common factor here, factor it, and then do greatest common factor one more time, you'll be back here. So let's look at that. Greatest common factor of 6x squared and 8x. X, definitely, and 2. So 2x specifically. So 2x comes out, and then I've got some parentheses. 2x times what is 6x squared? 3x. 2x times what is 8x? 4. And the cool thing about this method is now that we have 3x plus 4, over here, when you factor this, you should get the same thing in parentheses. What do 21 and 8 have in common? 7. And in fact, that's minus 21 and minus 28. So it's actually minus 7. And you get 7 times what is 21x? 3x. Negative 7 times what is negative 28? 4. See, they match. And now again, you just do greatest common factor all over again. And so the greatest common factor now is just 3x plus 4. So 3x plus 4 comes out, and you're left behind with 2x minus 7. Okay, so that's how you factor. We are going to do a few more examples. This is probably a good place just to kind of take a breather. And then we're going to come back to this. All right. So I hope your break was awesome. And if you're wondering, yeah, I had to stop and teach a whole class, but here I am back and we're going to do another example. So example 2, again, we're still factoring. And it's this idea of the AC method, so-called because you find A, B, and C. But I think from this point forward, it'll probably be a little more concrete. So, for example, we'll call this example 2. And we're going to do 18x squared minus 15x minus 63. Okay, so at first glance, just my initial thoughts. If the numbers look big, it's probably because they are. And sometimes the terms we'll have like a common factor that you can take out at the beginning. So think of greatest common factor, like is there a greatest common factor here? And technically that's always your first step. Like even on the problem I showed you in example 1, had there been a greatest common factor at the very beginning, we could have factored it out, but there wasn't. But if there is, you should do that, because basically when you take the greatest common factor out, what's left behind is just easier to do because you have smaller numbers. So when you have to do the whole A times C, what numbers multiply to give me this and add to give me this, you're working with smaller numbers, so you're more likely to find your answer. So if I look up here, 18 is divisible by 3, 15 is divisible by 3, 63 is divisible by 3. So I'm going to use that to my advantage, basically. So if I factor out a 3, it looks like this. And now, instead of factoring this up here, and my A being 18, my B being negative 15, and my C being negative 63, I'm going to factor what's in this parentheses, because understand, by taking out the 3, like I did here, this is still equivalent. Like it's still the same equation, so-called, because I just put an equal sign there. But I mean, it's still the same expression. I just pulled out that 3. And I did that to help me whenever I start trying to actually factor this and break it into pieces. So I'm going to label this now. Remember, this is like, you look at this as standard form. In standard form is, you know, I'll do an arrow. Y equals ax squared plus bx plus c, just to kind of remind you. So I'm just going to label A, B, and C here. So A is this, B is this, C is this. Now what I'll usually tell students in classes to do, if you can do it this way, fine, by all means. But if it helps you to be like, my A is 6, my B is negative 5, and my C is negative 21, then do that. You know, write them down, that way you don't forget. Anyway, so our challenge, I mean, is going to be the same thing here. Basically, I need to break this up so that I can factor it completely and get us to fully factored form. In other words, I need to figure out what was multiplied to do this. And basically that just comes down to, I need to rewrite this middle term somehow. Like I need negative 5x to be written as 2 different terms, but I have no idea what they are. Like that could be negative 6 plus 1. That could be negative 10 plus 5. Literally infinite number of possibilities. And we don't need an infinite number of possibilities. We need something very specific and to the point. So I'm going to use the X to do this just because I think it is pretty nice to keep you organized. And actually, I'm going to put it down here. So make my little X. And remember, A times C goes on top, B goes on bottom. Well, A times C in this case is going to require my calculator because I don't know what 21 times 6 is off the top of my head. Except I do now that I think about it. I think it's 126, but anyway. The point is, you may not know what it is. It is 126. So A times C is 6 times negative 21. So it's negative 126. And then your B is literally just whatever B was, negative 5. And remember, we're just trying to find 2 numbers that add to give me this negative 5 and multiply to give me that negative 126. And I mean, as far as there being a shortcut, there really isn't. This is, if anything, this is the long part. And sometimes it's long, sometimes it's not. It just depends on what number you get, what product you get when you do A times C. This is negative 126. It's a bigger number, so it's going to have more factors. I don't know how long it'll be before we find the 2 factors that add to give me negative 5, but we're going to do it. I'm going to skip the times 1 because it's not times 1. 126 divided by 2, though, is 63 times 2. That's negative 2 and 63. That's 2 factors. They do not add to negative 5. And I'm just going to keep going. 126 divided by 3 is a negative 3 and a 42. They don't work. 126 divided by 4 does not work. It doesn't divide evenly. 126 is not divisible by 5. Let's divide it by 6. We get 21. What about negative 6 and 21? They do not add to give me negative 5. All right. 126 divided by 7 is 18. Awesome, it's divisible by 7. I didn't even know that, but that still doesn't add to give me -5. So 126 divided by 8 doesn't divide evenly. 126 divided by 9 is 14, and I think that's what we need. So -9 and 14, if I add those together, I would get 5, but I need -5. So I'm not going to have -9 and 14. I'm going to have +9 and -14. And you can do that because the only way you multiply to get a negative is if you have a negative and a positive. I was just doing this with all my negatives down this side, but you can put the negative on this side and let the number on this side be positive. Still gives you the same product, but it does change what they add to. So 9 and -14, it turns out, is what we needed. So again, if anything, that's the part that takes some time. Now we're in business. I'm going to do something that I used to do. And a lot of times I tell students not to do this, but I also never really explained it this way. This little 3 out here, we're going to leave it, but we can't forget about it. Like, it's there. We don't need to forget that it's part of our problem, because when we go to have factored form, that's part of it. But basically, we've already got the front of our final answer, if you will. We got the first part of it. But I'm just going to rewrite what's in parentheses by itself over here, and we're just going to factor it. I'm going to actually put these terms down here. Remember, A was 6, B was -5, C was -21. I'm going to erase that just so I've got more room. And now, like, I'm just about to power through this, so follow me. And honestly, if you want to try this based off that other problem, try it. See if you can get the answer, which would mean you pause the video. All right, I'm going to keep going. So 6x squared minus 5x minus 21. I want to know how to split this middle term, and it's these numbers that tell me how to do that. So this 5x, this minus 5x, is going to become 2 different terms, specifically a 9x and a -14x. And then I just bring down the other terms. And now I just do greatest common factor twice and I'm done. So I look at my first 2 here. I see that they have 3x in common, so that's what I'm going to factor out. 3x times 2x is how I get 6x squared. 3x times 3 is how I get 9x. I'm going to close those parentheses. Now I'm going to look at this, and if assuming I did this correctly, this parenthesis should have 2x plus 3 in it. All right, what does 14 and 21 have in common? 7. That's -14, that's -21, so it's a -7. And so -7 times what is -14? 2x. -7 times what is -21? 3. Does this problem look familiar to y'all? It should. It's the same one we just did a moment ago. But I wanted y'all to see what it looked like if we were just told to factor it. So you get this, but remember, you had that 3 in the beginning. So it goes here, and you're done. That's your answer. So again, we technically had the same exact problem before. I just wanted you to realize it just didn't have the 3 in the beginning. But again, this technically is how you would work the factored problem. I just don't want you getting confused and think that you're going to like multiply at the beginning every time. No. I just wanted y'all to realize that technically we are undoing multiplication here. All right, we are going to go on to another example now. I'm going to erase all of this. You can pause the video and write it down if you need to. So we're going to dive straight on to example 3, as I'm going to call it. I'm just going to leave this set up because we're going to need all of this. Obviously, it'll be different numbers, but all right. So example 3 is 8x squared plus 22x minus 21. So if I just look at that right now and go ahead and check it for a greatest common factor, I don't believe there is one. The 21 is really what helps you with that, because the only things that multiply to 21 are 7 and 3, and these are not divisible by 3. or 7. So same as with our previous problems. You know, if I knew how to split 22x up right now, we could just split it, factor it, and be done, but we don't know. So we're going to label this to find our A's, B's, and C's. A is 8, B is 22, C is negative 21. Okay, so again, A times C is whatever 8 times negative 21 is, which is not particularly nice. It's negative 168. And B is just 22. All right, so what I've written here is negative 168 because we need to find the factors. And I started filling in our little X chart here. Again, we're trying to find numbers that multiply to negative 168, but add to 22. And the way we do that is by factoring 168. So 168, I mean, at this point, I'm not going to go down everything because like I can look at that and know that 168 divided by 2, whatever I get, yeah, it's factors, but they're not going to add to give me 22. So I'm going to start it like divided by 4, and that works, meaning negative 4 times 42 is negative 168, but that doesn't add to give me 22. 168 isn't divisible by 5, so I'll try 6, and you get 28 and 6, which does work. Negative 6, positive 28, there's my answers. So see, on this problem, we actually got what we needed on the second try. Now, yeah, I jumped ahead to negative 4, but again, you can do that. Like you can try smaller numbers, meaning like numbers less than 10, but you don't necessarily have to start at 1 or 2 if you don't think they're going to work. So negative 6 and 28 are our numbers, and I'm going to put it over here just for consistency like I did on the last problem. So 8x squared plus 22x minus 21. I'm not going to color code this anymore though, because I want y'all to see like how this would look like if you were actually writing it on paper. So I got negative 6 and I got 28. 8x squared plus 22x minus 21. So this is 8x squared. And remember, the whole reason why we found these numbers and why we fill them in on our little chart here is because this tells us how to break up this middle term to make that factoring possible. By the way, the factoring that we're doing right here, minus 6x plus 28x minus 21. Whenever we do this, it's called factoring by grouping because you're grouping the first 2 terms and you're grouping the last 2 terms and you're looking for a greatest common factor. 8x squared and 6x have a 2 in common. They have a 2x in common. So 2x times 4x is how we get this. 2x times negative 3 is how we get that. And remember, if we did this correctly, then whatever shows up in parentheses here under this part should match. 28 and 21, what do they have in common? 7. That's a positive 28, so I'm pretty sure it's just going to be a plus 7. 7 times what is 28? 4x. Again, it should match. All right, so then this should be minus 3. 7 times minus 3 is minus 21. All right, last but not least, you just factor the greatest common factor again, which is now that 4x minus 3. And we get 4x minus 3 and 2x plus 7. And that is your answer in factored form. Oh, by the way, this was example 3. I think I forgot to put that on there. And now last but not least, I'm going to give y'all one more example, and this one is kind of rough. And I just want y'all to kind of see, notice I'm erasing everything now for this next example, and I'm going to erase my title too, because I want to have this whole board to do this. And I'm not doing this to like intimidate y'all, but I do want y'all to just kind of see how you can get a problem that's kind of ugly, but it doesn't mean it's impossible to do. So example 5, hope I didn't like lose count, but I actually found this problem. I think I mentioned it earlier in an old textbook, and I liked it because this is what you're given, and you're told to factor it. You're told to write the answer in factored form. Well, that thing is written in vertex form, which we talked about briefly at the beginning of like the first video. So if it's vertex form, remember this actually helps us graph this parabola, but we're trying to factor it. So actually this is incredibly unhelpful because now we need to, I mean, obviously you need like a plan of attack, but essentially your plan of attack here is going to be, I need to multiply out this a minus 3 to then combine this minus 4 into it and then try to factor it. So let's do that. Equals 4, a minus 3, a minus 3 minus 4. This part is equals 4. And I'm just going to do parentheses, that way you know it's together. That's a squared minus 6a plus 9 minus 4. And now you, again, it's like we're just going. Now you got to distribute. So that's 4a squared minus 24a plus 36 minus 4. Okay. So now you actually have this written in a way where you can do that minus 4. So you're going to do that minus 4 and you get 4a squared minus 24a plus 32. And now it's like, now that we did all that, now we can actually factor this. So this is the beast that we need to factor. And remember, it wasn't up here, but I mean, factor was what we're doing. So we want to factor this one. I'm going to do our little XY chart again. But first I want to point out, to check for your greatest common factor, there is one. So specifically, each one of these numbers is divisible by 4. So actually we can rewrite this now. We can factor out the 4 and we get a squared minus 6a plus 8. Which means we can actually just factor what's inside here, because we know our answer at the end is going to have like a 4 in front of it. So let's just factor what's inside of this. Again, I'm going to use our little x. Remember, you need a times c, you need b, and kind of running out of space down here. I'm just going to put it at the top on the other side. This one's actually really simple to factor, so despite it starting kind of ugly, it's really, really simple to factor. So I'm just going to write a squared minus 6a plus 8 up here. And remember, you need a times c, you need b. Well, a here, and don't let it confuse you because that's a squared. This is where you've got like double a's. And the a, b, c here refers to standard form, not the fact that the variable a is being used here. And if that's going to confuse you, simple solution. Go over here and use a different variable. Just make that x. Not a big deal. Works out the same way. But in any case, a, as in standard form, refers to, remember, the number in the front, which would be a 1 technically. So a equals 1. Your b is that middle term, negative 6. It's the number part. It's the coefficient part of your middle term. And c is your last number there, which is 8. So a times c is 1 times 8, which is 8, and b is negative 6. So this is where you really don't even need to create a chart for this. I mean, what two numbers multiply to give you 8, but add to give you negative 6? And I mean, if you can't think of it, it's okay because you haven't been practicing a lot, but it's 4 and 2, specifically negative 4 and negative 2. Negative times a negative is a positive. When you add those together, you get negative 6. Negative 4, negative 2. So a squared minus 4a minus 2a plus 8. And again, technically there's a 4 out there in front of it, but we're just pretending it's not there for now. But I went ahead and wrote it to the end so we don't forget it. Now to factor this, we're grouping. What does a squared minus 4a have in common? Only an a. What does this have in common? Only a minus 2. And that's a minus 4. Factor this again, you get a minus 2, a minus 4. And again, you technically had that 4. So your answer really is this. Okay. I want to point something out real quick. There was a shortcut here technically to factoring this that some of you, like right now, if I asked you to look for it, you might find it, you might not. But a minus 2 and a minus 4 here, like these numbers weren't just made up. The minus 2 and the minus 4 came straight from there. And the reason why you were able to do that on this one is because your a was 1. If a ever equals 1, then think about it. Like before we were saying what multiplies to give us a times c and what adds to give us b. Well, your b is still just like normal. But a times c before now, a has always been a bigger number. So you've wound up with having to multiply c by some bigger number that gives you something like that 168 we were trying to factor. Well, here, if a is 1, a times c is just technically just c. c is 8, and because a is 1, when I do 8 times 1, I've still just got 8. And basically, it just makes it easy because of that first number being 1. Since that first number is 1, it just mathematically, it works out. It's simpler. And basically, you can just ask yourself, all right, what two numbers multiply to give me 8, but add to give me negative 6? And if you come up with negative 4 and negative 2, you can jump straight to the answer. It's technically a shortcut. Sometimes whenever we're teaching algebra, we'll start with this method. We'll start with only examples where a equals 1, but I don't start with that because then students think that that's how it always works, and they won't do this part because they don't want to do the work. And it's like as soon as you get examples where there's a coefficient bigger than 1 in front here, this breaks. Like you can't just use the shortcut. So it's important that you understand how to do this part. And if you happen to come across one that is a shortcut, once you've learned this, then it's like, oh, cool, that's a gift. I'll just use it really quick and I'm done. All right. So that has been factoring. It's kind of like your crash course. If you wind up wanting more videos, just let me know. I can always do more examples, but this ought to give you a good bit of material to get going on. Thank you, everybody. Y'all take care.